In this video, we present an overview of our paper, PointInfinity, Resolution-Invariant Point Diffusion Models. Recent years have witnessed remarkable success in diffusion-based 2D image generation. And a key reason behind this success is the large amount of images available for training. In the 3D domain, the most abundant type of data is perhaps point clouds. However, diffusion-based 3D point cloud generation methods have lagged behind, lacking the realism and diversity of their 2D image counterparts. We believe that the central challenge is the substantial size of typical point clouds. Common point cloud datasets contain point clouds at the resolution of 100,000 or more. This leads to prohibitive computational costs for generative modeling due to the quadratic complexity of transformers. Consequently, several models are severely limited by computational constraints, often restricted to a low resolution of 2,000 or 4,000 points. In this paper, we propose an efficient point cloud diffusion model that is efficient to train and easily scales to high resolution generation. Our model, PointInfinity, is trained at low resolution, but generates much higher resolution at test time. What's more, we find this test time resolution increase improves the generation quality. Our intuition comes from the observation that different point clouds of an object can be seen as different samples from a shared continuous 3D surface. As such, a generative model that is trained to model multiple low-resolution samples from a surface ought to learn a representation of the underlying surface, allowing it to generate high-resolution samples after training. To encode this intuition into model design, we propose to decouple the representation of the underlying surface and the representation of point cloud generation. This decoupled design lies in the core of our model, the two-stream block, which is the main building block of our diffusion denoiser. The first stream of the two-stream block is the latent stream. It has a constant-sized memory and models the underlying surface. The second stream is the data stream, which represents the raw point cloud. It has variable size that depends on the point cloud resolution. We then design lightweight read and write modules for communicating between the two streams. The bulk of our model's computation is spent on modeling the underlying surface within the latent stream, and therefore invariant to the resolution. Our full denoiser is a stack of the two-stream blocks. During inference time, generating higher resolution point clouds simply means increasing the number of initial noise samples. When the point cloud resolution is high, we can extract continuous surface using marching cubes. We train PointInfinity on Code3D v2, which is a real-world 3D dataset consisting of noisy point clouds and RGBD images. PointInfinity uses RGBD images as condition and learns to generate the corresponding point clouds. For a quantitative evaluation, we use transfer distance and F-score to measure the shape quality, and PSNR to measure the color quality. We now present our main result of resolution scaling. As highlighted in the table, the generated surface of PointInfinity improves when generating higher resolution than training time. On the contrary, the surface quality of point E drops as the resolution goes higher. We see that color quality follows the same trend as shape quality. Similarly, in qualitative results, we see the performance of PointInfinity is better than other state-of-the-art methods. It also verifies that our generation improves as the resolution gets higher. We further compare PointInfinity with point E in terms of computational complexity. Thanks to the resolution-invariant property of PointInfinity, the training complexity stays constant regardless of the test time resolution. On the other hand, point E requires equal training and testing resolution and scales quadratically. At inference time, the complexity of PointInfinity is linear, while point E stays quadratic. This verifies the computational advantage of our model design. In conclusion, we present PointInfinity, the first resolution-invariant point diffusion model that efficiently generates high-resolution point clouds with state-of-the-art quality. This is achieved by a two-stream design, where we decouple the underlying surface from the raw point cloud representation. Interestingly, we observed that the surface quality improves as the resolution increases, and we thoroughly analyzed this in a paper. Please check out our paper for more details. Thank you.